Welcome to Space News from the Electric Universe, brought to you by the Thunderbolts Project at thunderbolts.info. In a recent Space News episode, Thunderbolts colleague, physicist Eugene Bagashov, offered his analysis of what is thought to be the first ever observed interstellar asteroid. As Eugene explained, the object's origin and behavior appear to offer no easy answers, either for standard astronomy or the electric universe. Today, Eugene continues his discussion with some new thoughts on the mysteries the asteroid has raised.
Let us continue our consideration of the so far unique object Oumuamua, supposed to be the first known interstellar asteroid. I'll remind that the previous episode was devoted to the somewhat problematic fact that although this object possesses a hyperbolic orbit, it does not demonstrate any cometary activity, which one might expect from the standpoint of the electric comet hypothesis. Later on in this video, I would propose another possible explanation for this from the electrical perspective, but first let us discuss the recent research paper devoted to Oumuamua. In this paper, the authors look at the actual spectroscopical data on this object, trying to make guesses about its surface composition following from its spectrum. In short, their conclusion is that it seems that the surface should be covered by some sort of carbon-rich substance, formed under prolonged exposure to the cosmic ray radiation in the interstellar medium. They also suppose that this substance might be thick enough to thermally insulate the interior of the object. So they conclude that in this case Oumuamua might actually have quite a high ice content, but the ices did not sublimate even at the perihelion because of this external insulation. Now, I don't have enough expertise in this area to judge whether they are correct in the assumption that the characteristic dark and slightly red color of Oumuamua is caused by organic compounds, but I wish to mention another paper from 2015 where the other group of researchers have tried to recreate the space weathering effects on silicate minerals in the laboratory conditions. Their results show that the darkening and reddening that is frequently observed on small bodies in the solar system might be caused by the particles of nanophase iron that form under the bombardment of energetic hydrogen ions. Essentially, what seems to happen is the disruption of the crystal lattice of the surface minerals, followed by their oxygen atoms forming hydroxyl groups and water molecules with the incoming hydrogen, which is the very same mechanism that is supposed to be the primary source of water in comets in the electric comet hypothesis. Thus, the iron from the surface minerals, having lost the binding to the oxygen, is being reduced to its metallic state, forming the mentioned nanoparticle grains. It is not impossible that this is the reason for the observed spectrum of Oumuamua and many other bodies, rather than the carpet of organic compounds. Anyway, the hypothesis of thermal insulation of Oumuamua's interior by the thick surface layer that the authors of the first paper propose seems to lend a helping hand to the dirty snowball model in explaining the lack of the activity of the object. Essentially, in this framework, Oumuamua might be just a regular comet, which means supposedly a piece of ice mixed with dust, but it is the prolonged exposure to the cosmic rays that have formed the insulating surface layer, which inhibits the sublimation, making the cometary activity impossible. Curiously enough, this seems to work for the electric comet hypothesis just as well. If the silicates on the surface of the rocky object would be buried under a layer of some organic molecules, perhaps one would also expect the lack of cometary activity, since there is no direct access of the incoming hydrogen ions to the oxygen in the silicates. I would suppose that the difference between these two scenarios is that in the electric comet hypothesis the required thickness of the organic layer would be less, since we just have to prevent the surface minerals from the direct contact with the solar wind. But in the snowball model, one would expect that a thicker layer would be required, as it must have enough durability to withstand the strong heating at the perihelion, which is impossible to achieve with only a thin layer of insulation. As a side note, this also means that the supposed age of the object in the electric comet perspective might be somewhat less, in the sense that one does not need billions of years of cosmic ray exposure to form only a thin veneer of organic compounds. It might happen much quicker than the formation of a thick layer required by the snowball model. To give you some numbers, the authors suppose that the insulating layer thickness might be somewhere in the range of 0.1 to 2 meters. Anyway, there is a noticeable problem with this hypothesis in the first place that the authors themselves acknowledge. It is the fact that the very same insulating layer should be formed also on the surface of the objects from a hypothetical Oort cloud around the Sun. These objects also should not demonstrate cometary activity if this is the case, supposedly being there for billions of years and accumulating the same carpet of organics. But this is absolutely incompatible with the observations, as the Oort cloud is supposed to be the reservoir of active comets, rather than inert objects insulated by the layers of organic compounds. So perhaps it is reasonable to take this whole research with a good pinch of salt. Now, moving to a slightly different topic. One very important thing that I've missed in the previous analysis was indicated by the people in the comments section, namely GM Trainer and Leo Caldas. In particular, it is the fact that the perihelion of Oumuamua strikingly coincided with an incredible uptick in solar activity. I'll remind you that the date of the perihelion was September 9th, 2017, and exactly the day before, on September 8th, the sunspot area peaked at 1760 millionths of a solar hemisphere. Last time such high area of sunspots was observed on December 19, 2014, at the very maximum of the current solar cycle number 24. But in September 2017, we were already halfway into the solar minimum, yet the spot's presence was just as pronounced. And not only that, but during the closest approach of Oumuamua, we've also had two strongest solar flares of the whole cycle, X 9.2 on September 6th and X 8.2 on September 10th. The first one was actually the strongest solar flare after the X17 flare on September 7th, 2005, almost exactly 12 years before. So somehow the perihelion of the only known interstellar object coincided with a significant maximum of sunspots and also the strongest flares in 12 years. In my opinion, this does not seem to be a simple coincidence. It is also worth noting that at the very same time, the strongest earthquake of this year happened, magnitude 8.2 on September 8th off the coast of Mexico. And it was also the time when two strongest hurricanes of 2017 have formed, Irma and Maria a week later. In my opinion, both the seismic and hurricane activity at that time was provoked by the increase in solar activity, which in its turn was triggered by the perihelion of Oumuamua. So I became curious about the frequency of such occasions. Maybe other significant solar optics also coincided with perihelia of some hyperbolic or parabolic orbits. I used JPL small body database to search for dates of perihelion passages of the known objects with parabolic and hyperbolic orbits in the recent years, namely since the beginning of the year 2011 and until the present moment. The other constraint I've used was the perihelion distance, that is, the distance to the Sun during the closest approach. For this, I arbitrarily chose the value of 2.2 astronomical units, which roughly corresponds to the inner border of the asteroid belt. So in the end, I was looking for objects that come from somewhere very far away, dive inside the area encircled by the belt only once, and then go away, never to return again, just like Oumuamua did. I've found 32 such objects with perihelia in the last 7 years. Then I went looking for the significant solar flares, where by significant I mean stronger than M6.0, and marked the days when these events took place in order to find correlation. I've identified 73 days when such flares happened in the last 7 years. I'm not an expert in statistics, so I might be wrong in my analysis, but in order to quickly analyze the possibility of correlation, I've calculated how much of the total time is covered by perihelia of these objects. I've set a time span of 15 days centered on the date of perihelion for every such object, such that if the flare happens in this interval, it is considered as a hit, and considering a miss otherwise. 32 times 15 gives us a maximum of 480 days spanned by these perihelion intervals, or about 19% out of total 7 years. So considering a completely random or at least uncorrelated distribution of both the flares and perihelia, we should expect about 19% of the flares to happen at these perihelia intervals. But in the actual data, I found that 29 out of 73, or about 40% of the days with significant flares, took place during these intervals. So it seems that the probability of a strong solar flare happening during the perihelion of an object on a hyperbolic or parabolic orbit is about twice as high than the one expected without any correlation between these events. We might also look at it the other way. Not all the 32 objects have actually had the significant flares during their perihelia, but only 17, or about 53% of the total number. So maybe there is some pattern in their orbital parameters or something else that might distinguish between the ones that have supposedly triggered the flares and the ones that haven't. So far, I've failed to find any such pattern, yet it does not mean that it is not there. I have highlighted the objects during the perihelia of which there were significant flares with yellow, hoping that maybe someone would be more successful than I was in this endeavor. So here we see the list of the objects and some of their orbital parameters, namely the name, q, which is the minimal distance to the Sun in astronomical units, orbital eccentricity e, inclination I, longitude of the ascending node and argument of the perihelion in degrees, and lastly the date of the perihelion in Julian days. For explanation of these parameters, I recommend watching my talk from the EU 2016 conference, which is available at the Thunderbolts Project YouTube channel. Now getting back to the original discussion about the anomalous lack of activity of Oumuamua during its perihelion, I wish to put forth another quite far-fetched hypothesis. I hope the viewer is not too tired of these yet. So, looking at the situation from the very simplified electrical perspective, one might suppose that what we observed was some sort of focusing of the electrical energy on one object rather than the other. I mean, we might suppose that there is a roughly equal amount of energy for each such perihelion passage, but this energy can be redistributed between the Sun and the object that is getting close to it. Just like the amount and location of electrical power release in a circuit might be adjusted by changing the resistances of its various components. So in this framework, the case of Oumuamua might represent one of the extremes, when almost all the power of the circuit is released at the Sun, and the other object remains inert, which is why we see strongest flares on our star and at the same time don't see any cometary discharge features at Oumuamua. Perhaps it might also solve the cases of these other objects that I've listed earlier. Perhaps those that didn't trigger any significant solar activity were simply too active themselves at the time. This represents an interesting avenue for further research. As for the possible factors determining the redistribution of activity, my best guess so far would be to look at the position of coronal holes and the heliospheric current sheet around the time of perihelion. High-speed solar wind streams from coronal holes with their open magnetic field lines essentially act as highways for charged particles, allowing them to quickly move from the external object to the photosphere of the Sun and vice versa. And the importance of the heliospheric current sheet in the electric perspective is kind of obvious already from its name. So, wrapping up, I wish to once again express my gratitude to all the people who participate in the discussion of this subject in a productive manner, noting such correlations, coincidences, and other patterns which might indicate that there is some sort of connection present between various phenomena in the solar system. I would like to encourage all of you to continue such search and to share your thoughts and the results of your research with others. Luckily, the electric universe paradigm represents a great framework for assembly of such crowdsourced research activities, and I hope it would bring some success in our search for the laws that govern the universe.
For continuous updates on space news from the electric universe, stay tuned to thunderbolts.info.